If you found your way here, you're probably looking for something soothing, interesting, and just the right amount of nerdy to help you drift off into a gentle sleep. And tonight, we're descending, very slowly and very carefully, into the warm, glowing depths of Earth's hidden heart. That's right, we're talking about volcanoes, magma, mystery, and a planet that likes to let off a little steam from time to time. Now I should offer a gentle warning. While this video is designed to relax you, I can't promise it won't accidentally pique your curiosity. If you find yourself sitting up in bed whispering, "Wait, did they just say lava can be both fast and slow?" then I suppose I've done my job a little too well. But don't worry, if you're wide awake at the end, at least you'll leave with a few fun facts tucked under your pillow. Before we begin, may I politely ask for a small favour? If you enjoy this kind of calming, curiosity-driven content, a like or a gentle tap on the subscribe button truly helps this sleepy corner of the internet continue to grow. And if you're feeling extra cozy, I'd love to know, where in the world are you listening from tonight? And what time is it where you are? Feel free to leave a comment below. I read them like bedtime stories. Now take a moment to settle in. Fluff your pillow, adjust your blanket, or nestle into that just right spot on the couch. Let your breath slow and your thoughts wander gently without urgency. We're about to explore a world of molten rock, deep pressure, and ancient fire. But don't worry, it's all at a very safe distance. No fireproof pajamas required. This video is intended for relaxation, entertainment, and educational purposes only. While we'll be talking about sleep and calming topics, nothing here should be considered medical advice. But if the soothing sound of lava cooling into rock helps you sleep, well, nature's doing half the work. Ready? Let's begin. If you were to peel back the layers of the Earth like a giant cosmic onion, you'd eventually come across something rather special. The birthplace of volcanoes. They don't come from nowhere after all. Every bubbling lava fountain, every ash-spewing mountain, and every quietly steaming vent is the surface expression of something deeper, something ancient, slow-moving, and very, very hot. But volcanoes don't just appear out of thin air like party tricks gone wrong. They grow, they form, they build themselves up patiently over time, shaped by forces both violent and subtle. And that story begins, quite fittingly, underground. Let's imagine the Earth as a layered sphere. At the centre is the solid inner core, mostly iron and about as toasty as the surface of the sun. Surrounding that is the outer core, a swirling sea of molten metal. And above that, we find the mantle, a vast, slow-churning region of rock that flows, not like water, but like an extremely thick and reluctant syrup. This is where things get interesting. Now, the crust, our home turf, is just the thin, brittle skin on top. If the Earth were an apple, the crust would be its peel. It floats atop the mantle, cracked into giant puzzle pieces we call tectonic plates. These plates shift, bump, and grind against each other, sometimes giving us earthquakes, sometimes forming mountains, and often, when conditions are right, birthing volcanoes. So how exactly does a volcano form? It all starts with magma, molten rock beneath the surface. When rock in the mantle gets hot enough, or when pressure decreases in just the right way, or when it gets infused with a bit of water, it can melt. This molten material, lighter than the solid rock around it, begins to rise. Slowly, persistently, like a bubble in a thick milkshake. This rising magma collects in reservoirs beneath the surface called magma chambers. Think of these like underground storage tanks, rooms full of pressurized molten rock, quietly waiting. And sometimes, when the pressure builds too high, or when a pathway opens to the surface, the magma erupts. But before we get too caught up in the action, let's take a step back and look at the architecture of a volcano, its anatomy, if you will. Because not all volcanoes look alike, and their structure can tell us a great deal about what's going on beneath the surface. At the base of it all is the magma chamber. This is where the molten rock gathers before an eruption. From there, magma travels upward through a conduit, a kind of volcanic highway, toward the surface. At the top, it often emerges through a central vent or sometimes multiple smaller side vents. The eruption forms a crater at the summit, and if the volcano has a particularly dramatic blowout, that crater can collapse into a wide depression known as a caldera. Calderas can be massive, spanning several kilometers across, and they often fill with water to become crater lakes, serene and deceptively peaceful. Surrounding this entire system is the cone, the part we see sticking out of the Earth like a pimple on the planet's face. But even this visible portion comes in many flavours. There are shield volcanoes, which are wide, gently sloping, and built mostly from runny lava flows. Think of Mauna Loa in Hawaii, one of the largest volcanoes on Earth. Shield volcanoes resemble overturned soup bowls, broad and smooth, the result of lava that spreads far and fast before cooling. Then there are stratovolcanoes, or composite volcanoes. These are the classic postcard-style volcanoes, tall, steep and dramatic. Mount Fuji in Japan, Mount Rainier in Washington state. These volcanoes are formed from alternating layers of lava, ash and rock fragments, building up over time into towering peaks. They're beautiful, majestic, and just a little bit moody. And then we have cinder cone volcanoes, the overachievers of the volcanic world. They're small, steep, and formed almost entirely from pyroclastic debris. That's a fancy term for the bits of rock and ash that get hurled into the air during an eruption and then rain back down to Earth. Cinder cones may not be large, but what they lack in size they make up for in enthusiasm. Of course, not all volcanoes play by the rules. There are complex volcanoes, fissure volcanoes, submarine volcanoes, and even ice-covered volcanoes hidden beneath glaciers. Some lie dormant for thousands of years, while others grumble and sputter on a regular basis. And each one tells a different story, shaped by its environment, its chemistry, and its personality. Yes, volcanoes have personality. Some are quiet and consistent, like those in Iceland, politely letting out lava with minimal fuss. Others are loud, explosive, and utterly unpredictable, prone to tantrums that can blanket cities in ash or send shockwaves around the world. But beneath all that drama lies a simple truth. Volcanoes are driven by pressure and density. Magma wants to rise because it is less dense than the rock around it. When it finds a path upward, it takes it. If that path is blocked, pressure builds. And when the lid finally pops, well, that's when we get an eruption. Interestingly, not all eruptions make it to the surface. Sometimes magma stalls in the crust and cools underground, forming what geologists call an intrusion. These hardened bodies of rock, like batholiths and laccoliths, can later be exposed by erosion, forming dramatic features like Yosemite's El Capitan or the Black Hills of South Dakota. It's like a volcano that never quite made it to the party, but left a gift anyway. Now, as you're lying there listening, you might be wondering, why do volcanoes tend to form in certain places and not others? And the answer lies with those shifting tectonic plates we mentioned earlier. Volcanoes love a good boundary. About 90% of all volcanoes form along tectonic plate edges. At divergent boundaries, where plates pull apart, magma rises to fill the gap, creating mid-ocean ridges and new seafloor. These submarine volcanoes are the most common type on the planet, quietly building new crust beneath the oceans. At convergent boundaries, where one plate dives beneath another, things get even more dramatic. The subducting plate carries water and minerals deep into the mantle, lowering the melting point of the rock above. The result? Magma, and lots of it. These subduction zones are responsible for the explosive volcanoes that ring the Pacific Ocean, in a region ominously known as the Ring of Fire. And then there are hotspots, plumes of heat that rise from deep within the mantle, burning through the crust like a blowtorch. These are not tied to plate boundaries and can create chains of volcanoes as the tectonic plate moves over them. Hawaii is a classic example. As the Pacific plate drifts, it creates a trail of volcanic islands, like footprints across the ocean floor. Each of these settings produces volcanoes with unique characteristics. Oceanic volcanoes often have basaltic lava, which is runny and tends to flow rather than explode. Continental volcanoes, on the other hand, can produce thicker, more silica-rich magma, which traps gas and leads to more violent eruptions. But regardless of where or how they form, volcanoes remind us that the Earth is not a static ball of rock. It's dynamic, restless, and very much alive. They are both destroyers and creators, reshaping landscapes, influencing climates, and even fostering new life. And perhaps most remarkably, they've been doing this for over 4 billion years, long before humans arrived to marvel at their power, or get nervous every time a mountain starts to smoke. So the next time you see a peaceful snow-capped volcano in the distance, or watch a video of glowing lava pouring into the sea, you'll know that there's more to that moment than meets the eye. That mountain isn't just sitting there. It's the tip of an ancient, slow-burning process that reaches deep into the Earth's core. A process that has helped shape continents, raise islands, and tell the story of our planet in fire and stone. And all of that, every plume of ash, every trickle of lava, every quiet rumble beneath your feet starts with the anatomy of a volcano. A chamber, a vent, and a whole lot of pressure, just waiting for the perfect moment to say hello. If volcanoes are the grand performances, the fireworks shows of geology, then magma is the backstage crew. Quietly powerful, always moving, and absolutely essential to the entire spectacle. Without magma, there would be no lava, no eruptions, no towering cones of rock. Just a very solid and somewhat unremarkable planet. Magma is molten rock, yes, but is also a story of heat, pressure, chemistry, and time. A story that begins deep beneath your feet, in a place most of us will thankfully never visit. Let's begin in the mantle. This layer sits beneath the Earth's crust and extends down nearly 3,000 kilometers. Unlike the outer core, which is liquid metal, the mantle is solid rock, but it behaves in a strange way. Over very long timescales, it flows. Not like water, not even like honey, but more like an incredibly thick putty that slowly deforms under pressure. The technical term is viscous, but think of it as Earth's very slow-moving lava lamp. Magma forms in the mantle, but not just anywhere. It's not bubbling away like soup in a cauldron. Most of the mantle is too solid and too cool to melt, but under certain conditions, like changes in pressure, temperature, or the addition of water, rock can begin to melt into magma. There are 3 main ways this can happen: decompression melting, flux melting, and heat transfer melting. Don't worry. We'll go through each of them as gently as possible. Decompression melting is the most common method. It happens when rock from deeper in the mantle rises toward the surface. As it rises, the pressure decreases, and when the pressure drops quickly enough, the rock doesn't have time to cool down, it just starts to melt. This is what happens along mid-ocean ridges, where tectonic plates are pulling apart and new ocean crust is constantly being created. It's like the Earth is exhaling molten rock into the sea, creating fresh land in the process. Very slowly, very quietly, and very persistently. Flux melting, on the other hand, is a bit more sneaky. It occurs at subduction zones, those places where one tectonic plate dives beneath another and sinks into the mantle. As the oceanic plate descends, it carries with it water and other volatiles trapped in sediments and minerals. When these materials are released into the surrounding mantle, they lower the melting point of the rock. Essentially, they act like antifreeze, allowing the rock to melt at lower temperatures. This newly formed magma is often rich in silica and gases, which means it's thick, sticky, and more likely to erupt explosively. Then there's heat transfer melting, which is kind of like melting an ice cube by dropping a hot coal on it. When very hot magma intrudes into cooler surrounding rock, it can cause that rock to melt as well. This usually happens near magma chambers, where one batch of magma heats up the rocks around it, potentially triggering even more melting and mixing. Now, not all magma is the same. In fact, magma comes in different types, depending on its chemical composition, particularly its silica content. Silica is a key ingredient. It influences everything from magma's viscosity to its tendency to explode. The more silica, the thicker and more sluggish the magma becomes. The less silica, the more fluid and fast-moving it is. There are three main categories of magma: basaltic, andesitic, and rhyolitic. Let's start with basaltic magma. It has the lowest silica content, usually around 45 to 55%, and is the most common type found at mid-ocean ridges and hotspots like Hawaii. It's very runny, which means it tends to flow easily and form wide, shield-shaped volcanoes. Basaltic magma produces those beautiful, glowing rivers of lava you see slowly oozing across the ground like syrup on a warm pancake. Next up is andesitic magma. This one has a moderate amount of silica, about 55 to 65%. It's thicker and cooler than basaltic magma, and usually forms at subduction zones. Andesitic eruptions are more dramatic, with lava that doesn't flow as easily and a tendency to trap gases. This combination can lead to explosive eruptions and tall, steep stratovolcanoes, the kind that look pretty in pictures and then remind everyone of their power with a sudden ash cloud or pyroclastic flow. And finally, we have rhyolitic magma. This is the diva of the magma world. With more than 65% silica, rhyolitic magma is thick, sticky and full of gas. It doesn't flow, it creeps, it seethes. It resents being underground, and when it erupts, it tends to do so with impressive flair. Rhyolitic eruptions can be truly catastrophic, launching massive amounts of ash into the sky and forming huge calderas. But they're also relatively rare, which is perhaps for the best. Temperature also plays a role in magma's behaviour. Basaltic magma is the hottest, typically ranging from 1000 to 1200 degrees Celsius. That's hot enough to roast marshmallows at a deeply unsafe distance. Rhyolitic magma is cooler, closer to 600 to 800 degrees Celsius, but more dangerous due to its explosive nature. It's a bit like comparing a calm campfire to a bottle of soda that's been shaken too hard and then opened near your favourite couch. Pressure too is important. As magma rises toward the surface, the pressure decreases, and gases that were dissolved under high pressure begin to expand. This is similar to opening a can of soda. As long as the can is sealed, everything is calm, but once you pop the top, especially if you've shaken it, those bubbles rapidly expand and escape. In magma, these bubbles are mostly water vapour, carbon dioxide and sulfur gases. If they build up too quickly and can't escape, they can cause the magma to explode in a dramatic and sometimes very inconvenient fashion. Now let's talk for a moment about magma chambers. These are underground pockets where magma collects and waits, sometimes for years, centuries, or even millennia before erupting. Magma chambers are not huge, open caverns filled with glowing lava, as they're often portrayed in cartoons. Instead, they are zones of partially molten rock surrounded by crystal mush and complex plumbing systems, more like a spongy, seething blend of heat and rock than a lava lake with floating skeletons. Over time, magma inside these chambers can evolve. Through a process called fractional crystallization, minerals begin to solidify out of the magma in a specific order. The remaining melt becomes enriched in silica and volatiles, which can make it more explosive. This process is like boiling down a sauce. What's left becomes thicker, richer, and sometimes more dangerous to serve. Sometimes different batches of magma mix together in these chambers. When hotter, more mafic magma intrudes into a cooler, silica-rich chamber, the result can be a kind of geological cocktail, complete with bubbles. This mixing can destabilize the system and trigger eruptions, especially if gas levels get too high. It's a bit like pouring soda into a glass of champagne and then shaking it. Not recommended. And if all of this seems a bit chaotic, that's because it is. Magma systems are notoriously complex and difficult to predict. We can model them, we can study them, but each one has its own quirks, its own chemistry, its own rhythm. Some volcanoes erupt frequently but gently. Others stay quiet for centuries, only to explode with devastating force. Yet through all this complexity, one thing is certain: magma is the engine behind every volcanic event. Whether it flows in lazy sheets across a landscape or erupts in towering columns of ash, it is the molten heartbeat of the Earth. It connects the deep interior with the surface, recycles the planet's crust, and plays a surprisingly big role in making Earth habitable. Volcanic gases released during eruptions help regulate the atmosphere. Lava flows create new land, and volcanic soil, rich in minerals, supports lush agriculture once everything has cooled down a bit. Magma may be hidden, mysterious, and hard to reach, but it's anything but irrelevant. It's a reminder that the solid ground we walk on is not as still or as silent as it seems. Beneath our feet, the planet is always at work, melting and moulding, storing energy and releasing it, crafting landscapes and rewriting maps. So the next time you see a plume of steam rise from a mountaintop, or a slow-motion video of lava tumbling down a slope, remember, it all started deep within the Earth. A spark of heat, a change in pressure, a little water in the right place, and suddenly a rock becomes a liquid, and the story of a volcano begins. All thanks to magma, the quiet artist working behind the scenes. There's something oddly satisfying about the idea of a volcano erupting. Not the destruction, of course, but the sheer theatricality of it. All that rumbling, smoke, ash and lava, as if the Earth itself had been holding in a cosmic sneeze for a few thousand years and finally let it out with dramatic flair. But not all eruptions are explosive, and not all of them come with fireballs and flying boulders. In fact, volcanoes have a surprisingly broad emotional range. Some whisper, others scream. Some flow like melted chocolate, others burst like overshaken soda bottles. And it all depends on one thing: the type of eruption. Let's start with the basics. A volcanic eruption happens when magma rises to the surface of the Earth and escapes. Sounds simple enough. But how it escapes, and what it does when it gets there, depends on the magma's composition, temperature, gas content, and viscosity. Viscosity, by the way, is just a fancy word for how thick and sticky something is. Honey has high viscosity. Water has low viscosity. Magma can range from pancake batter to peanut butter, and that texture makes all the difference. Take basaltic magma, for instance. It's hot, runny, and has low silica content. That means it flows easily and allows gases to escape without much fuss. Eruptions involving basaltic magma are usually effusive, which is a polite way of saying it just sort of seeps out. Picture gentle fountains of lava, glowing rivers crawling down a hillside, and lava lakes gently bubbling like a witch's brew on low heat. These eruptions are common in places like Hawaii and Iceland. They're beautiful, mesmerizing, and oddly peaceful, like watching molten candle wax, if the candle weighed several million tons. Then there's rhyolitic magma, which is the opposite in almost every way. It's cooler, much stickier, and absolutely packed with gases. As magma rises toward the surface, the pressure decreases and the gases begin to expand, just like bubbles in a shaken soda bottle. But if the magma is thick and viscous, those bubbles can't escape. They build up, they get agitated, and then, kaboom, an explosive eruption is born. These types of eruptions can launch ash, gas, and rock miles into the sky and flatten everything for kilometers around. They are the volcanic equivalent of slamming all the doors in the house at once. Andesitic magma, which sits between basaltic and rhyolitic, tends to produce eruptions that are somewhat intermediate in style. It's thicker than basaltic, so the gas doesn't escape quite as easily, but it's not quite as dramatic as rhyolitic magma. Think of it as magma with a bit of a temper, sometimes calm, sometimes testy, often unpredictable. Scientists have developed a scale to describe eruption intensity, called the Volcanic Explosivity Index, or VEI. It ranges from 0 to 8. A VEI of 0 is essentially a lava ooze, barely worth putting on shoes for. A VEI of 8, on the other hand, is what we might call seriously inconvenient. These mega eruptions can blast thousands of cubic kilometres of material into the sky and alter global climates. Fortunately, VEI 8 eruptions are extremely rare. The last known one occurred more than 26,000 years ago at Taupo in New Zealand, and before that, about 74,000 years ago at Mount Toba in Indonesia, which may have caused a global volcanic winter. In other words, not something we want to see too often. Let's take a closer look at the different types of volcanic eruptions, starting with Hawaiian eruptions. These are named after the volcanoes in Hawaii, particularly Mauna Loa and Kaslauea. Hawaiian eruptions are gentle and continuous, producing those iconic lava fountains and long glowing flows. The lava is low in viscosity, so it spreads easily, building up shield volcanoes that look like warriors' shields laid flat on the ground. These eruptions are often safe enough to watch from a distance, and even walk alongside. Just wear appropriate footwear and try not to trip. Next, we have Strombolian eruptions, named after Stromboli, a volcano off the coast of Italy. These are a bit more enthusiastic. They feature short, explosive bursts of lava and gas, often at regular intervals, kind of like a geological hiccup. Strombolian eruptions throw lava blobs, called volcanic bombs, into the air, but they're usually not too destructive unless you're standing in the wrong place at the wrong time. They create small cones of cinder and are often described as moderately explosive but highly photogenic. Then come Vulcanian eruptions, which are a bit more serious. These involve thicker magma and more pressure, leading to short but powerful explosions of ash and rock. The name comes from Volcano, another Italian island with a history of abrupt outbursts. These eruptions can produce shock waves, ash clouds, and pyroclastic flows, a term we'll get to in a moment, and not because it's fun. Next on the list are Plinian eruptions, named after Pliny the Younger, who witnessed the eruption of Mount Vesuvius in the year 79 and wrote about it in detail. These are the big ones. Plinian eruptions are characterized by tall columns of ash and gas that can reach the stratosphere, intense explosions and widespread devastation. They often come with pyroclastic flows, volcanic lightning, and enough ash to collapse rooftops miles away. These are the kinds of eruptions that leave cities buried for centuries and entire regions transformed overnight. And finally, we have the very rare and very dramatic ultra-Plinian eruptions, which rank at the highest end of the VEI scale. These are true planet shakers, capable of changing the climate for years, cooling global temperatures, and altering ecosystems. Thankfully, they're spaced out by tens of thousands of years. We've got time to prepare, or at least buy a better umbrella. Now, about those pyroclastic flows. If lava flows are the slow, glowing rivers of a volcano, pyroclastic flows are their hyperactive cousins. These are fast-moving avalanches of hot gas, ash, and volcanic debris that race down the sides of a volcano at speeds of up to several hundred kilometers per hour. They can destroy everything in their path and are extremely dangerous. The ancient city of Pompeii was buried by one. So was Saint-Pierre on the island of Martinique in the early 1900s. Pyroclastic flows don't just burn, they suffocate, crush, and bury. Think of them as volcanic avalanches, only much hotter and less polite. But eruptions don't just go sideways, they also go up. Volcanic ash, tiny particles of pulverized rock, can rise tens of kilometers into the sky. Once up there, it gets carried by wind, often travelling thousands of kilometers before settling back down. In large quantities, ash can clog airplane engines, damage crops, and turn sunny days into twilight. The 2010 eruption of Eyjafjallajökull in Iceland is a modern example. It grounded flights across Europe for days, all thanks to a relatively modest eruption that just happened to be in the right place at the right altitude. Volcanoes also produce gas, lots of it. Water vapour is the most common volcanic gas, followed by carbon dioxide, sulfur dioxide, hydrogen sulfide, and a few other trace compounds. These gases can influence weather and climate, and in some cases they pose a more immediate danger. Carbon dioxide is heavier than air and can collect in low-lying areas, creating invisible hazards. In 1986, a sudden release of CO2 from Lake Nyos in Cameroon killed over 1,700 people in nearby villages. The gas came from volcanic activity beneath the lake bed, which had been building pressure until it finally erupted, not with lava, but with gas. Sulfur dioxide, meanwhile, can combine with water vapour to form sulfuric acid droplets, which reflect sunlight and cool the Earth's surface. This is how large eruptions can lead to temporary drops in global temperature. The eruption of Mount Pinatubo in 1991, for instance, caused global temperatures to decrease by about 0.5 degree Celsius for several years. It's like the planet hit the snooze button and took a chilly nap. Not all volcanic material is dangerous, though. Some eruptions produce lava domes, blobs of thick, viscous lava that pile up over a vent like toothpaste slowly being squeezed out of a tube. These domes can grow steadily for months or years, sometimes collapsing and causing small eruptions or blockages. They're like geological bellyaches, uncomfortable, unpredictable, and prone to sudden release. And then there are lava fountains. These are exactly what they sound like. Vertical jets of molten rock shooting into the air, sometimes tens of meters high. Lava fountains are both mesmerizing and slightly absurd, like the Earth has decided to host a very slow-motion fireworks display. They're common in Hawaiian eruptions and often signal that magma is near the surface and rich in gas. Volcanic eruptions are not one-size-fits-all. They range from gentle oozes to apocalyptic explosions, and every variation tells us something about the magma, the environment, and the planet itself. They are part chemistry experiment, part pressure cooker, and part natural spectacle. And while they can be terrifying, they are also essential to the life of the Earth. They build land, release gases into the atmosphere, and remind us, every so often, that the ground beneath our feet is far more alive than it looks. So whether a volcano whispers or shouts, trickles or explodes, it is always doing something meaningful. It is expressing the inner workings of a dynamic planet, a planet with heat in its heart, pressure in its bones, and a talent for dramatic timing. There's something quietly powerful about the landscapes shaped by volcanoes. They don't always shout their presence with steam or smoke. Sometimes they whisper, a rounded hill here, a curious black sand beach there, a lake that shouldn't logically be sitting at the top of a mountain, and every so often you'll stumble upon a patch of ground that's warm when it shouldn't be, or see a valley carved not by water or ice, but by fire. Volcanic landscapes are some of the most fascinating, bizarre, and beautiful places on Earth. They tell the story of destruction and creation at the same time, a story etched into rock, moulded by molten forces and sometimes wrapped in a surprisingly lush coat of green. Let's begin with lava flows, the very basic building blocks of volcanic terrain. Lava can travel in different forms depending on its composition, temperature, and gas content. In Hawaii, for example, you'll often find pahuho lava, smooth, ropey, and shiny like fresh taffy. It flows slowly and cools into surfaces that are deceptively soft-looking, but are actually quite hard underfoot. Then there's lava, which moves more like a bulldozer full of hot gravel. It's chunky, rough, and makes walking across it an exercise in ankle sacrifice. Both types of lava flows can cover huge areas, reshaping entire landscapes over time. They cool into vast basaltic plains, often cracked into strange hexagonal columns as they shrink, like the famous Giant's Causeway in Northern Ireland. Some volcanic flows take a different path entirely, downward. Lava tubes form when the surface of a lava flow cools and hardens, while the molten lava underneath continues to flow. Eventually, the lava drains away, leaving behind long, hollow tunnels. These lava tubes can stretch for kilometers beneath the surface, some large enough to walk through. In fact, early Polynesians in Hawaii used them for shelter, and bats have long claimed them as quiet hangouts. They're nature's version of subway tunnels, but much older and significantly more orange on the inside. Volcanoes also build mountains, Shield volcanoes, like those found in Hawaii and Iceland, are formed almost entirely by flowing lava. Their eruptions are frequent but gentle, layering flow after flow over time to create wide, gently sloping giants. Mauna Loa, for instance, is one of the largest volcanoes in the world. If measured from its base on the seafloor, it's taller than Mount Everest. It doesn't look it, because its slopes are so gradual, but it covers an area larger than many small countries. In contrast, stratovolcanoes, also known as composite volcanoes, are the classic cone-shaped mountains that dominate landscapes and postcards alike. Built from alternating layers of lava, ash and rock fragments, they grow steep and tall, often snow-capped and majestic. Mount Fuji in Japan, Mount Rainier in Washington state, and Mount Mayon in the Philippines are prime examples. Their beauty belies the danger. They're often the most explosive and unpredictable of volcanoes. Then there are calderas. If a volcano is particularly explosive and decides to empty its magma chamber all at once, the structure above can collapse in on itself, forming a massive crater-like depression. Some calderas are so large that entire cities could fit inside them. Crater Lake in Oregon is a stunning example. It formed about 7,700 years ago after Mount Mazama exploded and then collapsed. Over time, the caldera filled with rain and snowmelt, creating one of the clearest and deepest lakes in the world. The lake's deep blue colour is almost hypnotic, a calm, reflective surface born from violent origins. Other calderas are not filled with lakes, but with life. Yellowstone, for instance, sits inside a supervolcano caldera, the result of a truly colossal eruption that occurred over 600,000 years ago. Today, it's a geothermal wonderland, full of geysers, hot springs, mud pots, and steaming vents. You'd never guess you were walking around on the scar of an ancient mega-eruption. Or perhaps you would, once the ground starts burping sulphur-scented steam. Speaking of geothermal features, volcanic areas are often teeming with them. Geysers are hot springs under pressure. Water seeps deep into the earth, heats up near magma, and then explodes back to the surface as steam. Old Faithful in Yellowstone is the most famous example, predictably erupting every 90 minutes or so like a hot punctual tea kettle. Then there are fumaroles, openings in the ground that vent steam and gas, often smelling strongly of rotten eggs thanks to hydrogen sulfide. And mud pots, which are essentially boiling puddles of acidic, bubbling mud, can resemble very confused chocolate fondue fountains. These features are more than just tourist attractions. They're windows into the inner workings of the Earth. They tell us that something hot and active lies below, still cooking away beneath the surface, and in some places that heat has been put to good use. Geothermal energy plants tap into this natural warmth to produce electricity, offering a renewable and relatively clean source of power. Iceland, which sits atop a volcanic hotspot and a mid-ocean ridge, gets a significant portion of its energy from geothermal sources. It's a place where you can bake bread by burying it in warm ground, and then relax in a geothermal spa with a view of a glacier. Truly multitasking Earth-style, some of the most dramatic volcanic landscapes are found at rift zones and mid-ocean ridges. These are places where tectonic plates are pulling apart, allowing magma to rise and create new crust. The Mid-Atlantic Ridge, for example, runs down the centre of the Atlantic Ocean like a giant seam. In Iceland, this ridge rises above sea level, splitting the island in two. You can actually walk between continents there, standing with one foot on the North American plate and the other on the Eurasian plate. It's perhaps the only place on Earth where you can get jet lag without leaving the gift shop. Then there are volcanic islands, entire land masses formed from the accumulation of eruptive material on the seafloor until they poke above the ocean surface. The Hawaiian Islands are a perfect example, a chain of volcanic peaks formed as the Pacific plate slowly drifted over a stationary hotspot. Each island in the chain is a bit older and more eroded than the last, moving northwestward like geological dominoes. This slow-motion island assembly line has been operating for millions of years, and it's still going. The next island in the chain, called Loihi, is currently growing underwater and might breach the surface in a few tens of thousands of years. Patience, as always, is a virtue in geology. And let's not forget about black sand beaches, one of the most striking features of volcanic coastlines. These beaches are formed when hot lava flows into the ocean, cools rapidly and shatters into tiny fragments. Over time, these fragments are ground down by waves into smooth jet black grains of sand. The result is a beach that looks like it was sculpted from ink. It's stunning, eerie, and a vivid reminder that even destruction can lead to beauty. Volcanic landscapes are also fertile. After the initial devastation of an eruption, life tends to return with surprising speed. The ash and lava break down into nutrient-rich soils that support lush vegetation. Crops like coffee, grapes, and bananas thrive in volcanic regions. Some of the most famous wine-growing areas in the world, including parts of Italy and Chile, owe their richness to ancient eruptions. Volcanic soil is essentially nature's multivitamin for plants. This process of ecological succession, where life reclaims the land, is a beautiful example of resilience. Pioneer species like lichens and mosses are often the first to arrive, slowly breaking down rock and preparing the ground for grasses, shrubs, and eventually forests. Within decades or centuries, a once barren lava field can be transformed into a thriving ecosystem. Birds return, insects buzz, trees take root in the cracks. It's as though the earth says, "Alright, I've made a mess, let's grow something new." Even underwater, volcanoes shape ecosystems. Hydrothermal vents, essentially underwater geysers, support entire communities of life in the absence of sunlight. These deep-sea environments, powered by volcanic heat, are home to giant tube worms, clams, and bizarre shrimp that thrive on chemosynthesis. Instead of using sunlight, they rely on chemical reactions with sulfur compounds to produce energy. These ecosystems are some of the most alien and fascinating on our planet, and they're fueled entirely by volcanic activity beneath the ocean floor. So whether you're standing on a mountaintop soaking in a hot spring, walking across a lava field, or exploring a black sand beach, you're interacting with a landscape born of fire. A landscape that is always changing, always moving, albeit on a timescale far beyond our own. Volcanic landscapes are more than just dramatic scenery. They're reminders of the Earth's inner workings, of the balance between destruction and creation, and of the incredible power hiding just beneath the surface. They show us that even in the wake of fire and ash, life finds a way, that beauty can rise from the depths, and that the ground beneath our feet has stories to tell if we're quiet enough to listen. The Earth has always had a bit of a temper. Long before humans arrived on the scene with their houses, cities, and inexplicable fondness for socks with sandals, our planet was already busy erupting, collapsing, and rearranging itself like an indecisive interior decorator with access to magma. Volcanoes have been shaping Earth's surface for billions of years, writing their stories not in ink but in layers of ash, basalt, and obsidian. And while their eruptions may seem like sudden, fiery outbursts, they're actually just chapters in a very, very long book. To understand the history of volcanoes, we need to go back, way back. Picture a time when Earth was young, still cooling from its chaotic formation, constantly bombarded by meteorites and covered in a sea of molten rock. This was over 4 billion years ago during the Hadean, which sounds appropriately dramatic. It was a time when the crust was still forming, the atmosphere was thick with carbon dioxide and other volcanic gases, and the first oceans were just beginning to appear. Volcanoes in those early days weren't the neat cones we see today. They were more like endless fissures, spewing lava across the surface in sheets. As the Earth's crust stabilized and tectonic plates began to shift, volcanoes became more organized. By around 3.5 billion years ago, volcanic islands and proto-continents were already rising from the seas, shaped by underwater eruptions and cooling lava flows. These early volcanic landscapes provided the raw materials for life to begin. In fact, many scientists believe that hydrothermal vents, those deep-sea volcanic structures that spew hot, mineral-rich water, may have played a role in the origin of life itself. The combination of heat, water, and chemistry created a sort of planetary soup kitchen, serving up the molecules that would eventually become living organisms, no aprons necessary. Volcanoes have been involved in some of the planet's biggest changes and most dramatic turning points. Some of them were gentle giants, building land slowly over time. Others were more explosive in their personality. Among the most famous events in volcanic history are the massive flood basalt eruptions, huge outpourings of lava that covered thousands of square kilometers and changed the climate on a global scale. Take the Siberian traps, for example. About 250 million years ago, during the end of the Permian period, this enormous volcanic province erupted over what is now Siberia. It wasn't a single dramatic explosion, but rather a prolonged period of lava flows that lasted for nearly 1 million years. The result? An area roughly the size of the United States was buried under layers of basalt. More importantly, the gases released during this event, including carbon dioxide and sulfur dioxide, triggered climate changes that contributed to the largest mass extinction in Earth's history. Over 90% of marine species and 70% of land species vanished. It's known as the Great Dying, and it wasn't caused by a single volcano having a bad day, but by an extended, grumpy volcanic episode that threw Earth's ecosystems into disarray. Then there's the Deccan Traps in India, which erupted around 66 million years ago. This flood basalt event coincided closely with the extinction of the dinosaurs, and while a certain asteroid tends to steal the spotlight, many scientists believe that the Deccan eruptions played a major supporting role. The vast quantities of volcanic gas released would have altered the atmosphere, cooling the planet and acidifying the oceans. Whether the volcanoes set the stage or simply added insult to celestial injury, they were definitely part of the show. Not all significant volcanic events come with mass extinction attached. Sometimes they just leave behind jaw-dropping geological features. Around 74,000 years ago, Mount Toba in Indonesia erupted in what is now recognized as one of the largest volcanic events in human prehistory. This super-eruption ejected an estimated 2,800 cubic kilometers of material, enough to bury the entire United Kingdom under several meters of ash. It created a caldera over 100 kilometers wide and may have triggered a volcanic winter, with global temperatures dropping by several degrees for years. Some researchers have even speculated that the Toba eruption may have created a genetic bottleneck in early human populations, although that idea is still up for debate. Speaking of humans, let's take a moment to appreciate just how long we've been living with volcanoes, and occasionally being rudely reminded of their presence. One of the earliest recorded eruptions to impact a human civilization was that of Thera, now known as Santorini, in the Aegean Sea. Around the year 1600 BCE, this volcano erupted with extraordinary force, likely contributing to the decline of the Minoan civilization on nearby Crete. The eruption generated tsunamis, blanketed the region in ash, and created a massive caldera that today holds the iconic blue waters of Santorini's crescent-shaped bay. The eruption of Thera was so powerful and widespread that it has been suggested as a possible source for the legend of Atlantis, a once great civilization swallowed by the sea. While there's no conclusive evidence to support the myth, it's a testament to how volcanic events have been woven into our stories, our fears, and our imaginations for thousands of years. Fast forward to the year 79 CE, and we arrive at one of the most famous volcanic eruptions in recorded history, the eruption of Mount Vesuvius in southern Italy. On a warm summer day, the residents of Pompeii and Herculaneum were going about their business, entirely unaware that their local mountain was about to dramatically quit its day job as a scenic backdrop and resume its true calling as a fire-spewing menace. Vesuvius erupted violently, sending a towering column of ash, pumice, and gas into the atmosphere. Pyroclastic flows followed, racing down the slopes and burying entire towns in superheated debris. The cities were lost for centuries, preserved in ash like a time capsule of Roman life. What makes Vesuvius especially haunting is the suddenness of it all. People were frozen in the middle of daily activities, cooking, writing, relaxing. It's a chilling reminder that volcanoes may sleep for long periods, but they never forget how to wake up. Vesuvius has erupted many times since, and it remains one of the most closely monitored volcanoes in the world. It sits near a densely populated region, and its history makes it a prime candidate for future excitement, hopefully the kind we can predict and prepare for. Volcanic history isn't just about massive explosions. Some volcanoes erupt quietly and continuously, playing the long game. Kilauea in Hawaii, for example, erupted almost non-stop from 1983 to 2018, adding new land to the island with each flow. Rather than sudden destruction, this kind of activity reshapes the landscape bit by bit, offering a living demonstration of how the Earth builds itself up over time. But perhaps the most humbling thing about volcanic history is how little of it we've directly witnessed. The Earth has been erupting for billions of years, and humans have only been taking notes for a tiny fraction of that time. Most of what we know comes from studying rock layers, analysing ash deposits, and peering into ancient craters. It's geological detective work, piecing together clues from deep time. Volcanoes have influenced the climate, the composition of the atmosphere, the shape of continents, and even the course of evolution. Without them, the world would look very different, and quite possibly be uninhabitable. Volcanic activity helped release water vapour and gases into the atmosphere, creating the conditions for oceans and weather. They've enriched soils, formed islands, and provided the minerals that life depends on. They are, in many ways, Earth's original sculptors, reshaping the planet long before humans ever held a chisel or drew on a cave wall. Their story is not one of random explosions, but of patterns, cycles, and deep planetary rhythms, like the breathing of a planet. Long, slow, sometimes noisy breaths. So the next time you walk across a volcanic landscape or see footage of an eruption on the news, remember that you're witnessing just one frame of a very ancient film. One that has been playing since the Earth was born, full of fire, pressure, and the occasional plume of ash that catches the sun just right. Volcanoes are not just geological features, they are storytellers. Their layers are chapters, their eruptions punctuation marks. And while we may not always like the way they tell their tales, especially when they get a bit loud, they remain some of the most powerful, persistent, and poetic forces shaping our world. Some volcanoes are shy. They mumble, they grumble, they puff out a little steam and then go back to sleep. Others are flamboyant performers, all ash columns and lava fountains, demanding the world's attention like a diva in a red dress at a black and white party. And then there are the legends, the ones that left their mark not just on the landscape, but on history, culture, and memory. Their names are etched into textbooks, myths, and cautionary tales. They have reshaped coastlines, buried cities, and cooled the very skies above. These famous eruptions remind us that volcanoes are not just geological features, they are events, moments, turning points. Let us begin with one of the most iconic volcanic events in human history, the eruption of Mount Vesuvius in the year 79 of the Common Era. Nestled near the Bay of Naples in Italy, Vesuvius had been quiet for centuries. So quiet, in fact, that the people living nearby had forgotten it was even a volcano. It was just a mountain, a scenic backdrop to the vibrant Roman cities of Pompeii and Herculaneum. And then one day, the mountain roared back to life. It began with tremors, but the Romans didn't know that earthquakes could be linked to volcanic activity. They went about their lives, bathing, baking, debating, completely unaware that their world was about to be entombed in ash. When the eruption began, it launched a towering column of ash, pumice, and gas into the sky, reaching as high as 33 kilometers. For comparison, that's well into the stratosphere, where passenger planes like to cruise. The ash rained down relentlessly, burying rooftops and filling streets. Buildings collapsed under the weight. Those who didn't flee in time found themselves caught in pyroclastic flows, fast-moving avalanches of hot gas and debris that swept down the volcano's slopes at hundreds of kilometers per hour. These flows obliterated everything in their path, preserving the cities beneath layers of ash. Centuries later, when excavations began, archaeologists found people frozen in place, their final moments captured in haunting detail. Pompeii became a time capsule of Roman life, complete with mosaics, graffiti, and even the occasional loaf of carbonized bread. Mount Vesuvius has erupted many times since, but none so famously. Its 79 eruption remains a potent reminder of how quickly normal life can turn to ash, literally. Jump forward a bit over 1700 years to 1815, and we find ourselves facing the wrath of Mount Tambora in Indonesia. If Vesuvius was a drama, Tambora was an epic disaster movie with a very large budget and global consequences. When Tambora erupted, it was one of the most powerful volcanic events in recorded history. The eruption column soared 40 kilometers into the sky. The explosion was heard over 2,000 kilometers away, like hearing a firework in London from Rome. Tambora ejected an estimated 160 cubic kilometers of material into the atmosphere. That is enough to bury the entire United Kingdom in over half a meter of ash. But perhaps even more dramatically, it released vast quantities of sulfur dioxide gas, which combined with water vapour to form sulfate aerosols in the upper atmosphere. These aerosols reflected sunlight, leading to what became known as the Year Without a Summer. The year 1816 was marked by crop failures, food shortages, and unseasonably cold weather around the globe. Snow fell in June in New England. Famine struck parts of Europe and Asia. And in a villa on the shores of Lake Geneva, a group of writers trapped indoors by the gloomy weather decided to entertain themselves by telling ghost stories. One of them, Mary Shelley, began writing a tale about a scientist who reanimates the dead. You might know it as Frankenstein. That's right. One of the most influential horror novels ever written was, in part, inspired by a volcanic eruption on the other side of the world. Then there's Krakatoa, another Indonesian titan, which erupted in 1883 with such ferocity that it blew most of the island apart. The explosion was heard over 4,000 kilometers away, reportedly as far as the island of Rodriguez near Mauritius. The sound is often cited as the loudest in recorded history. The eruption generated tsunamis over 30 meters high, killing over 36,000 people. Some estimates are even higher. Ash from Krakatoa's eruption circled the globe, causing spectacular sunsets and altering weather patterns for months. It's said that the eerie red skies depicted in Edvard Munch's painting The Scream may have been inspired by the post-Krakatoa sunsets he witnessed in Norway. Once again, a volcano had reached across the planet, leaving its fingerprint on both nature and art. In more recent times, one of the most well-documented eruptions occurred in the United States, Mount St. Helens in Washington State, 1980. Unlike the previous examples, this one came with the full scrutiny of modern science. Geologists had been monitoring the volcano, which had been showing signs of unrest. Earthquakes, steam vents, and a growing bulge on the north side of the mountain that suggested magma was pushing its way to the surface. On the morning of May 18th, a magnitude 5.1 earthquake triggered a massive landslide, the largest in recorded history, which removed the north flank of the mountain. This sudden release of pressure unleashed a lateral blast, flattening forests for over 500 square kilometers and sending ash as far as the Midwest. 57 people lost their lives, including volcanologist David A. Johnston, who famously radioed the words, "Vancouver, Vancouver, this is it," moments before the blast reached his observation post. The eruption of Mount St. Helens taught scientists a great deal about volcanic behaviour, eruption forecasting, and the importance of heeding the warnings of an increasingly restless mountain. It also demonstrated how quickly a landscape could change. Before the eruption, The summit stood at nearly 3,000 meters. Afterwards, it was missing over 400 meters of elevation, carved away by the explosion. Another famous and somewhat tongue-twisting eruption took place in Iceland in 2010. Eyjafjallajökull, a glacier-covered volcano, erupted beneath ice, melting it rapidly and sending a plume of ash high into the atmosphere. While the eruption itself was relatively modest compared to Tambora or Krakatoa, its impact was outsized, especially for air travellers. The fine volcanic ash spread across European airspace, leading to the cancellation of over 100,000 flights and stranding millions of passengers. It was a reminder that even small eruptions can cause big disruptions in our interconnected world. Iceland is no stranger to volcanic activity. The island straddles the mid-Atlantic ridge, where two tectonic plates are slowly pulling apart. This geological setup makes it a hotspot for eruptions and for spectacular otherworldly landscapes. Volcanic activity has played a major role in shaping the island's terrain, from black sand beaches to moss-covered lava fields to geothermal spas. It's a place where volcanoes are part of the culture, the history and the plumbing. Other eruptions have been famous not for their violence, but for their persistence. Kilauea in Hawaii erupted continuously from 1983 to 2018, creating new land, destroying homes and offering a living, breathing example of how volcanoes work over time. Tourists flocked to watch lava pour into the sea, steam hissing as molten rock met cool ocean water. Despite the occasional road being swallowed by lava, the eruption was largely predictable and well monitored. And then there's Mount Etna in Sicily, one of the most active volcanoes in the world. Etna has been erupting for hundreds of thousands of years and shows no signs of stopping. It has lava flows, ash eruptions, and glowing fountains that light up the night sky like nature's own pyrotechnic display. Yet people have lived on and around it for millennia, growing grapes, olives, and lemons in the rich volcanic soil. It's a relationship based on respect, patience, and a healthy dose of optimism. Each of these famous eruptions teaches us something different. Some reveal the raw, unimaginable power of the earth. Others show how volcanic activity can ripple through ecosystems, economies, and even literature. Some remind us of the risks of living near a volcano. Others highlight the resilience of communities that rebuild and thrive in the shadow of a peak that sometimes huffs and puffs. Volcanoes are part of our shared story. They are both ancient and immediate, beautiful and dangerous, destructive and generative, and when they erupt, whether with a whisper or a roar, they leave behind more than just ash. They leave questions, legends, lessons, and occasionally a very confused airline schedule. So the next time you hear a name like Vesuvius or Krakatoa, don't just think of eruptions. Think of the people who live nearby, the scientists who study the warning signs, the sunsets painted in crimson and gold, the novels written by candlelight during a year without summer, and the quiet reminder that beneath our feet the earth is always thinking, sometimes loudly. It's easy to think of volcanoes as places to avoid. They spit lava, belch ash, and occasionally flatten entire towns. Not exactly the warmest welcome mat, and yet throughout history, people have flocked to volcanic regions, not just visited them, lived there, farmed there, raised families there, built temples, palaces, even entire cities in their shadows. So what gives? Why do humans keep setting up camp on the slopes of mountains that sometimes explode? As it turns out, volcanoes are not just agents of destruction, they're also surprisingly generous. In fact, some of the most fertile, resource-rich and geologically stable areas on Earth are directly linked to past or present volcanic activity. If you don't mind the occasional smoke plume or rumble, volcanoes make for pretty good neighbours. Temperamental, yes, but undeniably rewarding. Let's start with the soil. Volcanic soil, or andesol, is one of the most fertile types of soil on the planet. When lava and ash break down over time, they release a rich mix of minerals, like potassium, phosphorus, calcium and magnesium, that plants absolutely love. This natural buffet supports everything from vineyards to rice paddies to banana groves. That's why you'll find some of the world's most productive agricultural regions in places that have been touched by fire. In Indonesia, for example, the slopes of Mount Merapi and Mount Bromo are lined with green terraces and bustling farms. In Italy, the fertile plains around Mount Vesuvius have been farmed for thousands of years. The region produces tomatoes, grapes, olives and lemons that owe much of their flavour to the mineral-rich soil. In fact, if you've ever enjoyed a pizza with San Marzano tomatoes or a glass of wine from the slopes of Mount Etna, you've already tasted the legacy of a volcano. Spicy, mineral-laced, and possibly a little dramatic. But it's not just about farming. Volcanic regions also provide access to hot springs and geothermal energy. In places like Iceland, this geothermal energy is harnessed to provide electricity and hot water for entire towns. Pipes run under streets to keep them ice-free, and homes are heated by the natural warmth of the earth. It's efficient, renewable, and remarkably low in carbon emissions, all thanks to the volcanic activity bubbling quietly beneath the surface. Hot springs themselves are a major draw, both for their therapeutic benefits and their scenic beauty. People travel from all over the world to soak in mineral-rich pools heated by magma below. In Japan, these onsen are an important part of the culture. In New Zealand, geothermal areas like Rotorua offer not just relaxation, but also geysers, mud pools and steaming vents to marvel at while you lounge. It's like being at a spa hosted by a dragon. Volcanoes also offer a wealth of mineral resources. Many valuable metals and minerals are concentrated by volcanic processes, including copper, gold, silver and lithium. These materials form in hydrothermal veins or in the remains of ancient volcanic systems. In countries like Chile and Peru, mining operations target old volcanic deposits to extract the metals that power our electronics, infrastructure, and, increasingly, electric vehicles. Even pumice, a volcanic rock that floats on water and feels like a hardened sponge, is harvested for use in abrasives, construction, and skincare. Yes, that exfoliating footstone in your bathroom may very well be a tiny piece of an ancient eruption. But perhaps one of the most underrated reasons people live near volcanoes is simple. They've always been there. Volcanoes are not sudden newcomers. Many of them have been around for hundreds of thousands or even millions of years. Entire civilizations have grown up around them. Their presence becomes part of the identity of a place, woven into its myths, its architecture, even its cuisine. In Naples, for instance, Vesuvius looms as both a guardian and a warning. It's ever-present but mostly calm. People have learned to live with it, to respect its moods, and to prepare, just in case. Similarly, on the island of Java in Indonesia, volcanoes are part of daily life. They are prayed to, studied, and climbed for recreation. In Hawaii, Pele, the goddess of volcanoes, is a revered and complex figure, both creator and destroyer. Stories about her explain lava flows, eruptions, and the formation of new land. These cultural connections add a layer of meaning to the geological activity. The volcano isn't just a mountain. It's part of the story of who people are. And speaking of new land, volcanoes are excellent at making more of it. When lava enters the ocean, it cools rapidly and solidifies, slowly extending the coastline. In some places, entire islands have formed from volcanic eruptions. The Hawaiian Islands are a chain of volcanic peaks rising from the sea. Each island is essentially a volcano, or several, that built itself up over millions of years. These islands are now home to over 1 million people, with cities, roads, forests and beaches all sitting atop ancient lava flows. Even on a smaller scale, eruptions can reshape the land in ways that people find useful. New beaches, cliffs and hot springs can emerge after an eruption. Over time, what was once a barren lava field becomes colonized by plants, then animals, and eventually people. Nature moves in, and humans follow. Of course, there's always the risk. Living near a volcano comes with the understanding that it might one day erupt. For some, that's a manageable risk. They monitor the mountain, Stay informed and have evacuation plans. In Japan, for example, volcanic activity is closely tracked by the Japan Meteorological Agency, which issues alerts when signs of unrest appear. In Italy, Vesuvius is under constant watch by the Osservatorio Vesuviano, the oldest volcanological observatory in the world. Scientists look for patterns, earthquakes, ground deformation, gas emissions that might indicate magma is on the move. In some places, entire communities have had to be relocated. The town of Armero in Colombia was destroyed in 1985 by a lahar, a deadly volcanic mudflow, triggered by the eruption of Nevado del Ruiz. Over 20,000 people died, and the tragedy served as a grim reminder of how dangerous volcanoes can be when warnings go unheeded. Since then, efforts to improve monitoring and communication have become central to volcanic risk management. But even after such events, people often return, sometimes because they have nowhere else to go, sometimes because the land is too valuable to abandon, and sometimes because it's home, ash and all. Tourism is another reason people live near volcanoes. Volcanoes attract millions of visitors each year, drawn by the promise of dramatic landscapes, hiking trails, and the chance to witness Earth's raw power up close. Towns near volcanoes often depend on this steady stream of adventurers. Restaurants, guides, gift shops, and hotels all benefit from the volcano's presence. Mount Fuji, for example, sees hundreds of thousands of climbers each year. Mount Bromo, with its sunrise views and otherworldly terrain, is one of Indonesia's most popular tourist destinations. Of course, tourism can be a double-edged sword. While it brings in revenue, it also increases the risk to life and infrastructure if an eruption occurs unexpectedly. Managing access and ensuring safety becomes a complex balancing act. But for many communities, the volcano is both challenge and opportunity, a looming mountain that gives as much as it takes. There's also something psychological about the appeal of living near a volcano. For some, it's the thrill, the awareness of living on the edge, of coexisting with a force of nature that operates on a different timescale. For others, it's the beauty. Volcanic regions are often visually stunning, with mountains, valleys, lakes, and clouds of steam casting dramatic silhouettes at sunrise and sunset. The danger is part of the charm. Like keeping a tiger as a roommate, you respect its space, admire its power, and always sleep with one eye open. And then there's the mystery. Volcanoes remind us that we don't fully control the world we live in, that beneath our roads and cities the earth is still moving, melting, and sometimes murmuring. They reconnect us with a deeper sense of time and place, with the knowledge that everything solid was once in flux, that even the ground beneath our feet has a pulse. Living near a volcano isn't for everyone. It requires a blend of practicality, optimism, and perhaps a touch of defiance. But for those who do, it offers a life that is deeply rooted in the rhythms of the planet. A life shaped by soil, steam, and the occasional rumble underfoot. And maybe, just maybe, a life enriched by the knowledge that the mountain outside the window isn't just scenery, it's history, energy, and possibility, all rolled into one smouldering, majestic peak. Predicting a volcanic eruption is a bit like trying to guess when a notoriously moody friend is going to throw a tantrum. Sometimes they're calm and collected, other times they're clearly about to explode. And occasionally, just when you think everything's fine, they go full drama queen and cancel brunch with a lava fountain. But unlike brunch, volcanic eruptions can have enormous consequences, which is why scientists, known as volcanologists, spend their days and nights listening to the deep, rumbly whispers of the earth, trying to predict what comes next. So how exactly do you predict a volcano? Unfortunately, volcanoes don't come with countdown timers, flashy warning signs, or polite, about to erupt, please evacuate notifications. But they do give clues. The challenge lies in spotting them early enough, interpreting them correctly, and convincing everyone else that those clues matter. And in the world of volcanology, those clues come from four main areas: seismic activity, ground deformation, gas emissions, and thermal changes. Let's start with the ground shaking. Earthquakes are one of the most common signs that a volcano might be waking up. As magma moves through the Earth's crust, it fractures the surrounding rock, producing small tremors. These aren't the big, building-rattling earthquakes you might see in a disaster movie. Many are tiny, only detectable by sensitive instruments known as seismometers. But what they lack in drama, they make up for in importance. A sudden increase in the number and intensity of these quakes, especially directly beneath a volcano, can indicate that magma is on the move. There's even a particular kind of earthquake called a harmonic tremor, which is associated specifically with the movement of magma. It's a bit like the deep hum of a cello string being bowed, smooth, continuous, and very telling. When seismologists detect harmonic tremors under a volcano, they pay close attention, because it often means that magma is pushing its way toward the surface, like a slow-moving but determined guest trying to crash a very exclusive garden party. The second big clue is ground deformation. When magma accumulates beneath a volcano, it doesn't just sit quietly in a chamber like a well-behaved dinner guest. It pushes outward. This pressure causes the ground above to bulge, crack, or shift, sometimes dramatically, sometimes subtly. Scientists use a range of tools to measure these changes, including GPS receivers, tilt meters, and satellite radar systems. GPS units are incredibly precise. They can detect ground movement as small as a few millimeters. Tilt meters, on the other hand, measure changes in the angle of the land. Imagine placing a marble on a table and watching it start to roll as the table tilts. Satellite radar systems, particularly INSAR, short for interferometric synthetic aperture radar, are especially powerful. They send radar waves from space to detect tiny changes in the Earth's surface over time. It's like giving the planet a regular checkup from orbit. All these tools help volcanologists detect when a volcano is inflating, literally swelling up like a balloon. Mount St. Helens, for example, famously developed a visible bulge on its north flank in the weeks leading up to its 1980 eruption. The bulge grew at a rate of over 1.5 meters per day, until it eventually collapsed in a massive landslide, triggering the eruption. Spotting that kind of deformation early can provide a critical warning window. The third clue comes from gases. As magma rises toward the surface, the pressure decreases, and gases that were dissolved in the molten rock begin to escape. These gases include water vapor, carbon dioxide, sulfur dioxide, and hydrogen sulfide. Each of these gases tells scientists something different. Sulfur dioxide, for example, is particularly useful. An increase in sulfur dioxide emissions can signal that magma is nearing the surface and degassing as it rises. To measure volcanic gases, scientists use instruments placed directly on the volcano, as well as airborne sensors on drones or helicopters. There are also satellite-based systems that monitor gas plumes from space. The data is analysed not only to determine gas concentrations, but also to detect changes over time. A sudden surge in gas emissions can be a red flag, especially if it's combined with seismic activity and ground deformation. And then there's temperature. Magma is hot, very hot, usually between 700 and 1200 degrees Celsius. As it rises toward the surface, it heats the surrounding rock and can cause an increase in temperature at the surface, particularly around fumaroles, hot springs, and vents. Scientists use thermal cameras and infrared sensors to monitor these areas. An increase in surface heat might indicate that magma is closer to the surface than before. Now, none of these signs, on their own, is a guarantee that a volcano will erupt. Magma can rise and stall. Gases can vent harmlessly. Earthquakes can rumble for weeks without leading to an eruption. That's what makes forecasting so difficult. It's not about one clue. It's about the pattern, the timing, and how all the clues fit together. It's like playing a game of geological detective, where the volcano is always changing the rules. To make sense of it all, volcanologists rely on monitoring networks and alert systems. These networks collect real-time data from volcanoes around the world and feed it into models that assess risk levels. Based on this data, volcanoes are assigned an alert level, typically ranging from green, normal, to yellow, showing signs of unrest, to orange, heightened activity with potential eruption, and red, eruption imminent or ongoing. These alerts are issued by national geological agencies and are often shared with civil defense organizations, governments, and the public. In the United States, the United States Geological Survey manages these alerts. In Japan, it's the Japan Meteorological Agency. In Italy, the Osservatorio Vesuviano monitors Vesuvius and other Italian volcanoes. These institutions work closely with local authorities to make sure that if people need to evacuate, they can do so in time. Of course, prediction isn't just about science, it's also about communication. One of the hardest parts of managing volcanic risk is convincing people to take warnings seriously. Human behavior is complex. Some people want to wait and see. Others have lived near the volcano for generations and trust their instincts more than instruments, and some simply have nowhere else to go. There have been tragic cases where warnings were ignored or misunderstood. In 1985, the eruption of Nevado del Ruiz in Colombia triggered a lahar, a deadly volcanic mudflow that buried the town of Armero, killing over 20,000 people. Scientists had issued warnings, but delays in communication and reluctance to evacuate led to disaster. On the other hand, there are success stories. In 1991, Mount Pinatubo in the Philippines began showing signs of unrest. Scientists from the Philippine Institute of Volcanology and Seismology, along with experts from the United States Geological Survey, carefully monitored the volcano and issued timely warnings. Tens of thousands of people were evacuated before the eruption, which turned out to be one of the largest of the 20th century. Thanks to good forecasting and clear communication, thousands of lives were saved. And it's not just about sudden eruptions. Volcano monitoring can also help manage long-term hazards, like chronic gas emissions, ground instability, or slow-moving lava flows. In Hawaii, for instance, volcanologists have developed detailed hazard maps showing areas most at risk from future lava flows. These maps help guide development decisions and emergency planning. Volcano forecasting continues to improve with advances in technology. Machine learning, remote sensing, and real-time data analysis are opening new possibilities. Some researchers are even exploring how animals might react to volcanic unrest, though this area remains largely anecdotal. Elephants fleeing before earthquakes? Birds going quiet before eruptions? Maybe. But until we teach squirrels how to operate seismometers, we're probably better off sticking with the instruments. Still, for all the progress, predicting eruptions is not an exact science. It's an art as much as a science, a blend of data, experience, and intuition. Volcanologists spend years studying specific volcanoes, learning their unique behaviors, quirks, and personalities. Some volcanoes give lots of warning. Others are more reserved. Some are like chatty toddlers, always rumbling but rarely erupting. Others are the strong, silent types, quiet for centuries, then suddenly erupting with very little warning. Despite the challenges, the effort is worth it. Predicting volcanic eruptions saves lives, protects infrastructure, and helps us understand one of the most powerful natural forces on the planet. It's a reminder that we don't have to be powerless in the face of nature. With careful observation, good science, and clear communication, we can live alongside volcanoes, not without risk, but with respect and readiness. So the next time you see a puff of steam rising from a mountaintop, or read about a volcano showing increased seismic activity, remember that there's a team of scientists somewhere, carefully watching, measuring, analysing, and probably debating whether it's time to move from yellow to orange. They're not predicting the future, they're reading the signs, listening to the earth, and doing their best to keep us safe in a world where the ground occasionally breathes fire. When most people imagine a volcano, they picture a mountain, usually cone-shaped. may be snow-capped and belching a dramatic plume of ash into the sky. But not all volcanoes follow the script. In fact, many of the Earth's most active and abundant volcanoes are nowhere near dry land. They lie deep beneath the waves, hidden from view, quietly shaping the ocean floor and giving rise to some of the strangest and most extreme ecosystems on the planet. Welcome to the world of underwater volcanoes, where the lava is hot, the pressure is intense, and the neighbours include tube worms and bacteria that eat hydrogen sulfide for breakfast. Earth's oceans cover over 70% of the planet's surface, and beneath those blue depths lies an extraordinary volcanic landscape. In fact, the vast majority of volcanic activity on Earth occurs under the sea, along what's called the mid-ocean ridges. These ridges form where tectonic plates are pulling apart, allowing magma to rise and form new ocean crust. It's a slow but relentless process, a kind of deep-sea assembly line producing fresh sea floor at a rate of about 2 to 10 centimetres per year. It's not exactly speedy, but over millions of years it adds up. The most famous of these ridges is the Mid-Atlantic Ridge, which stretches like a seam along the ocean floor from the Arctic all the way down to near the southern tip of Africa. This immense underwater mountain range is dotted with volcanoes, fissures, and rift valleys. If you could drain the Atlantic Ocean, you'd see a jagged spine of volcanic peaks and valleys taller than the Alps, running like a backbone through the ocean basin, and the Mid-Atlantic Ridge is just one of several such systems. There's also the East Pacific Rise, the Indian Ridge, and a number of smaller rift zones scattered across the ocean floor. The magma that erupts at these mid-ocean ridges is usually basaltic, meaning it's low in silica and very runny. When it comes into contact with the near-freezing water of the deep sea, it cools rapidly and forms pillow lava, bulbous, rounded structures that look like overcooked dumplings or very lumpy marshmallows. These pillow formations are the underwater equivalent of lava flows on land, and they are a key part of how new ocean crust is built. But not all submarine volcanoes are quiet builders. Some are more dramatic. There are underwater eruptions that send ash and pumice up through the water column, forming temporary islands or altering coastlines. In 2012, for example, an underwater volcano erupted near Tonga, spewing pumice that formed a floating raft the size of Manhattan. Sailors described sailing through a sea of floating rocks, an eerie, surreal experience, like navigating a foamy, stony slush. Sometimes, underwater volcanoes do more than just bubble and fume. They build entire islands. This process is how many island chains have formed, especially those in the Pacific Ocean. The Hawaiian Islands, for instance, are the result of a volcanic hotspot on the Pacific Plate. As the plate moves slowly northwestward, the hotspot remains stationary, creating a trail of islands over millions of years. Each island in the chain represents a different stage in the life of a volcano, from active and steaming to eroded and dormant, and finally to sunken and submerged seamount. A seamount is a mountain rising from the ocean floor that doesn't quite break the surface. There are thousands of these across the ocean basins, many of them extinct volcanoes. Some of these seamounts become atolls, ring-shaped coral reefs that form around a sinking volcanic island. Over time, the central peak erodes away, leaving behind a circular lagoon fringed by coral. It's a beautiful ending to a volcanic life cycle, a sort of tropical retirement for a once fiery mountain. But perhaps the most fascinating aspect of underwater volcanoes isn't the lava or the islands, it's the life. In the cold, dark depths of the ocean, where sunlight never reaches, volcanic activity gives rise to hydrothermal vents. These vents, often found along mid-ocean ridges, spew superheated, mineral-rich water into the sea. The water comes from seawater that has seeped into the ocean crust, been heated by magma, and then re-emerges carrying dissolved metals and chemicals. The result is a black smoker, a vent that releases dark, cloudy plumes of mineral-rich water that can reach temperatures of over 350 degrees Celsius. Surrounding these vents are ecosystems unlike anything else on Earth. Giant tube worms, some over 2 meters long, cluster in writhing masses. They have no mouths, no digestive systems, and no eyes. Instead, they host symbiotic bacteria that convert the vent's chemicals into energy through a process called chemosynthesis. It's like photosynthesis, but without the sun. Alongside the tube worms are clams, shrimp, crabs, and weirdly translucent fish, all adapted to thrive in extreme pressure, complete darkness, and toxic chemicals. These ecosystems don't rely on sunlight, they rely on volcanoes, and they may offer a glimpse into how life began on Earth, or how it might exist elsewhere in the universe. Some scientists believe that life on Earth may have originated at hydrothermal vents. The combination of heat, water, and minerals could have created the perfect conditions for organic molecules to form and evolve. It's a compelling idea, that our distant ancestors were not land-dwelling creatures at all, but microbes living near an underwater volcano, sipping on hydrogen sulfide and enjoying the occasional burst of warmth. Underwater volcanoes also have an important role in regulating the chemistry of the oceans. As they erupt and interact with seawater, they release trace elements and nutrients that influence marine ecosystems. They play a part in the long-term carbon cycle, sequestering carbon dioxide in seafloor rocks and affecting global climate over geological timescales. Studying underwater volcanoes isn't easy. It's dark down there, it's cold, the pressure is intense, and GPS, as you might expect, doesn't work very well under several kilometers of water. To study these hidden giants, scientists use remotely operated vehicles, or ROVs, which are robotic submersibles equipped with cameras, sensors, and sample collectors. These underwater robots can withstand crushing pressures and transmit data back to the surface in real time. There are also autonomous underwater vehicles, or AUVs, which can be pre-programmed to explore specific areas and map the seafloor in high resolution. These machines have helped scientists identify hundreds of previously unknown volcanoes and gain insight into how the ocean floor is constantly evolving. Despite all this technology, we've only explored a small fraction of the ocean floor. It's estimated that there are over 1 million submarine volcanoes, but most remain uncharted. Every year, researchers discover new vents, new seamounts, and new life forms. It's like an alien world right here on Earth, one that's constantly shifting, bubbling, and surprising. And occasionally those underwater eruptions come closer to the surface. In 1963, off the coast of Iceland, a submarine eruption broke through the ocean and formed a new island called Surtsey. Scientists rush to protect it from human interference and study how life colonizes a brand new landmass. Over time, mosses, birds, and insects arrived, offering a rare opportunity to observe ecological succession from the very beginning. Surtsey remains a protected scientific reserve to this day, a living laboratory born from fire and sea. Submarine volcanoes don't just affect local ecosystems, they can also trigger tsunamis if they erupt violently enough. While rare, underwater eruptions that displace large volumes of water can send shock waves across ocean basins. This is one reason scientists monitor both land and sea for signs of volcanic activity. The more we understand about what's happening beneath the waves, the better prepared we can be for the unexpected. And the unexpected is part of the charm. Underwater volcanoes are full of mysteries. Why do some erupt quietly while others explode with force? How do organisms survive in such extreme environments? What role do these volcanoes play in Earth's long-term climate stability? These are questions that researchers are still trying to answer. But one thing is certain. Volcanoes aren't limited to mountaintops and tropical islands. They're also hiding in the deep, deep blue, shaping the world in ways we're only beginning to understand. They build new crust, support strange life, influence ocean chemistry, and remind us that the Earth is always changing, often in places we can't even see. So the next time you gaze out over the ocean and imagine calm waters and distant horizons, remember that beneath those waves lies a whole other world. A world of fire and water, pressure and chemistry, silence and suddenness. a world where volcanoes wear diving suits and the lava flows in the dark. When you think of volcanoes, your first thought probably isn't space. Perhaps it's lava, or ash, or how fast can I get away from one if it starts rumbling? But space, that seems like a stretch. And yet, volcanoes are not an Earth-exclusive phenomenon. In fact, our entire solar system is a volcanic playground. From the scorched plains of Venus to the icy moons of Jupiter, volcanoes, both familiar and bizarre, are scattered across the planets, and they're satellites like cosmic breadcrumbs. If Earth's volcanoes are the main act, the solar system is the extended universe, with all kinds of thrilling spin-offs. Let's start right here in our cosmic backyard, the Moon. Our Moon, serene and silver in the night sky, was once far more dramatic. It may not look it now, but much of the Moon's surface was shaped by ancient volcanic activity. Those dark patches you can see with the naked eye, they're called Luna Maria, Latin for seas, and they're vast basaltic plains formed by lava flows billions of years ago. Back then, the Moon was still warm enough inside to produce magma, which welled up through fractures in the crust and spread out in enormous sheets. Today the Moon is volcanically dead, a geologically quiet world. But its pockmarked face is a monument to its fiery past. From the dead silence of the Moon, let's jump to somewhere far more dramatic. Io, one of Jupiter's largest moons. Io is, without exaggeration, the most volcanically active body in the entire solar system. It's a world that looks like it was painted by someone who ran out of normal colours halfway through. Yellows, oranges, reds, and greens, all swirled together like a psychedelic fever dream. But Io's strange surface isn't just for show. It's covered with hundreds of volcanoes, some of which are actively erupting right now. Unlike Earth, Io's volcanic activity isn't powered by internal heat from radioactive decay. Instead, it's driven by tidal forces. Io is caught in a gravitational tug-of-war between Jupiter and its neighbouring moons, Europa and Ganymede. These constant gravitational squeezes cause Io's interior to flex, stretch and heat up, a process known as tidal heating. It's a bit like repeatedly bending a paperclip until it gets hot. Only in this case, the result is not a broken office supply, but plumes of molten sulphur shooting hundreds of kilometres into space. One of Io's most famous volcanoes is Loki Patera, which isn't just a name borrowed from Norse mythology. It's also one of the most powerful volcanic features in the solar system. Loki regularly undergoes massive overturns of its lava lake, releasing tremendous amounts of heat. If you were to stand on Io, and let's be clear, you should absolutely not try, you would see towering plumes of volcanic gas rising into a pitch-black sky, occasionally backlit by the enormous presence of Jupiter looming overhead. Not to be outdone, Venus offers its own volcanic resume. Often called Earth's sister planet due to its similar size and composition, Venus is a world wrapped in thick clouds and coated in mystery. We can't see its surface in visible light, but radar imaging from missions like NASA's Magellan spacecraft has revealed a land of rolling plains, highland plateaus, and an astonishing number of volcanoes. Estimates suggest that Venus has over 160,000 volcanoes, although most are small. That's a lot of volcanic activity, even for a planet with a reputation for being difficult. Venus's volcanoes come in a variety of shapes and sizes: shield volcanoes, pancake domes, and coronae, which are large, ring-like structures believed to be formed by upwelling magma. The interesting part: while we haven't seen any eruptions directly, some researchers believe Venus might still be volcanically active today. Fluctuations in atmospheric sulfur dioxide levels, thermal anomalies on the surface, and changes in radar reflectivity have all hinted at recent eruptions. In 2023, scientists using data from the Magellan mission found compelling evidence that a volcanic vent had changed shape between two radar observations, suggesting an eruption may have occurred. In other words, Venus might still be throwing temper tantrums behind those sulfuric acid clouds. Now let's head to the red planet, Mars. Mars has long fascinated scientists and science fiction fans alike, and for good reason. It's home to the tallest volcano in the solar system, Olympus Mons. This towering giant stands nearly 22 kilometers high, about 2.5 times the height of Mount Everest. Its base is roughly 600 kilometers wide, and its caldera is large enough to swallow an entire city. If you stood on the flank of Olympus Mons, the slope would be so gentle that you might not even realize you were on a mountain. Olympus Mons is a shield volcano, formed by repeated, highly fluid lava flows. But here's the twist. Mars doesn't have tectonic plates. On Earth, volcanoes like Mauna Loa and Mount Etna are eventually moved away from their magma sources by the shifting crust. But on Mars, the crust doesn't shift in the same way. That means a hotspot can keep feeding lava to the same location for millions of years, allowing volcanoes like Olympus Mons to grow to monumental proportions. Mars also has other impressive volcanic features, such as the Tharsis Ridge, a vast volcanic plateau that hosts several other giant volcanoes, including Arsia Mons, Pavonis Mons, and Ascraeus Mons. These massive structures suggest that Mars was once geologically active, and perhaps still is to some degree. There's even evidence of relatively young lava flows, meaning Mars might not be as quiet as it seems. Some scientists believe there could be intermittent low-level volcanic activity still occurring beneath its dusty crust. And speaking of dust, volcanic activity on Mars may have also played a crucial role in shaping its early climate. When Mars was younger, volcanic eruptions would have released carbon dioxide and water vapor into the atmosphere, gases that could have warmed the planet and supported liquid water on the surface. In this sense, volcanoes may have helped create conditions that were, at least temporarily, more Earth-like. Let's now move outward to the icy giants and their equally icy moons. At first glance you might think volcanic activity is off the menu here. After all, it's cold. But this is where things get interesting, because not all volcanoes spew molten rock. On some of these distant worlds, volcanoes erupt with water, ammonia, or methane instead. This phenomenon is known as cryovolcanism, or cold volcanism. Take Enceladus, a small moon of Saturn. It's barely 500 kilometers across, yet it's one of the most geologically intriguing objects in the solar system. At its south pole, Enceladus has a series of fractures nicknamed tiger stripes, from which plumes of water vapor and ice particles shoot into space. These icy eruptions are powered by tidal heating, much like on Io, and suggest the presence of a subsurface ocean beneath the frozen crust. The Cassini spacecraft flew through these plumes and confirmed that they contain water, salts, and organic molecules. That's right, organic molecules, the building blocks of life, being sprayed into space by a tiny moon around a gas giant. Not only is Enceladus volcanically active, it's also a compelling candidate in the search for extraterrestrial life. Then there's Triton, a moon of Neptune, which also shows signs of cryovolcanic activity. In the late 1980s, Voyager 2 captured images of dark geysers erupting from Triton's surface, reaching several kilometers into the sky. These eruptions are believed to involve nitrogen gas, released when sunlight heats subsurface deposits of frozen nitrogen. Even Pluto, once demoted from planet status but never from being interesting, may have cryovolcanoes. The New Horizons mission in 2015 revealed large dome-shaped mountains on Pluto that look suspiciously like icy volcanoes, perhaps once belching out slushy ammonia lava under a pinkish sky. These exotic volcanoes remind us that volcanic activity isn't limited to hot rocky planets. It can also occur in frozen worlds, powered not by magma, but by the slow grind of gravity, chemistry, and time. They expand our understanding of what volcanoes are, how they work, and where they might occur, even in places we once considered lifeless and inert. What all of this tells us is that volcanism is a fundamental process in shaping planetary bodies. It's a sign of internal energy, of active geology, and sometimes of habitability. Whether it's lava carving channels on Venus, water erupting from Enceladus, or sulfur painting the surface of Io, volcanic activity helps to renew, reshape, and sometimes even sustain a world. It also underscores the importance of continued exploration. Missions like NASA's Europa Clipper, set to launch soon, will investigate another moon with suspected cryovolcanism, Europa. Beneath its icy crust lies a vast ocean, and possibly hydrothermal vents similar to those on Earth's seafloor. If those vents exist, they could provide the energy and chemistry necessary for life. Future missions may even return samples from volcanic terrains on Mars, or map volcanic features in more detail on Venus. As our spacecraft get more sophisticated, and our questions more ambitious, volcanoes will remain central to the search, not just for geological understanding, but for life beyond our blue planet. So the next time you hear the word volcano, don't just think of Mount Etna or Kilauea. Think of ice geysers on Saturn's moons, sulfur lakes on Io, and lava plains on Venus glowing behind dense clouds. Volcanoes are not just Earth's story. They're a cosmic chapter in the tale of our solar system. Whether blazing or frozen, massive or microscopic, ancient or active, they remind us that even across billions of kilometers, planets and moons have their own pulses, their own tempers, and their own ways of breathing fire or ice into the universe. When a volcano erupts, it's easy to focus on the immediate spectacle: the glowing lava, the towering column of ash, the sky temporarily turning a dramatic shade of grey. But while eruptions can be dazzling in their fury and force, some of their most powerful effects are not visible at all. Volcanoes, as it turns out, have the ability to reach far beyond their slopes, even touching the atmosphere and influencing the global climate. In fact, they've done so many times throughout history, altering weather patterns, cooling the planet, and in some cases, creating years that felt like they belonged in a dystopian novel rather than the real world. To understand how this works, let's start with the basics. When a volcano erupts, it doesn't just release lava, it also hurls vast quantities of gas into the atmosphere, particularly water vapour, carbon dioxide and sulfur dioxide. Each of these gases behaves a little differently once it gets airborne. Water vapour is relatively short-lived and tends to contribute to local weather effects like rain or fog around the volcano. Carbon dioxide is a greenhouse gas, so over very long timescales, lots of volcanic eruptions could potentially contribute to global warming. But this is a slow process. Volcanoes emit only a small fraction of the carbon dioxide that human activities release each year. The real climate-altering culprit is sulfur dioxide. When this gas reaches the upper layers of the atmosphere, the stratosphere, it reacts with water vapour to form tiny droplets of sulfuric acid. These droplets are called aerosols, and they are incredibly good at reflecting sunlight. Essentially, they form a delicate global-scale mirror that bounces a portion of the sun's energy back into space. Less sunlight reaching Earth's surface means cooler temperatures, at least for a little while. The cooling effect from a major volcanic eruption can last anywhere from a few months to several years, depending on how much sulfur dioxide is released and how high it reaches in the atmosphere. If the eruption is small or confined to the lower atmosphere, the particles quickly fall out of the sky as rain or ash. But if it's powerful enough to punch through to the stratosphere, typically over 10 kilometers up, those particles can linger, sometimes circling the globe multiple times, and producing sunsets that would make a painter weep with joy. One of the most famous examples of volcanic climate influence occurred in 1815, when Mount Tambora in Indonesia erupted with astonishing force. This was not just your average bad day for a volcano, it was the most powerful eruption in recorded history. Tambora's eruption sent over 160 cubic kilometers of debris into the atmosphere and released massive amounts of sulfur dioxide. The following year, 1816, became known as the year without a summer. Across the northern hemisphere, temperatures dropped. Snow fell in June in parts of New England. Frosts ruined crops well into July. In Europe, persistent rain, failed harvests, and food shortages led to widespread famine and hardship. Grain prices soared, horses starved, prompting people to turn to bicycles as an alternative mode of transport. In Switzerland, a group of writers, confined indoors by unseasonably cold weather, passed the time by telling ghost stories. Among them was Mary Shelley, who penned a little tale called Frankenstein, all because a volcano on the other side of the world had thrown a massive fit. And Tambora wasn't alone. In 1883, another Indonesian volcano, Krakatoa, erupted with similar ferocity. While the eruption itself was cataclysmic, producing tsunamis and killing tens of thousands of people, its atmospheric effects were felt worldwide. The ash and aerosols from Krakatoa's eruption created vivid sunsets for years. Artists and poets were inspired by the brilliant blood-red skies. The temperature dropped by around 0.5 degrees Celsius globally, and weather patterns became erratic. Krakatoa showed that volcanoes, even those located on remote islands, have a passport to the entire planet. More recently, the 1991 eruption of Mount Pinatubo in the Philippines provided a textbook example of volcanic climate influence, this time in the age of satellites and modern instrumentation. Pinatubo ejected approximately 20 million tons of sulfur dioxide into the stratosphere, forming a thick aerosol layer that reduced global temperatures by around 0.5 degree Celsius for the next couple of years. This helped offset some of the global warming effects at the time, although the cooling was temporary. Pinatubo also confirmed what scientists had long suspected, that volcanic aerosols don't just cool the planet, they also affect precipitation patterns. As the Earth cools slightly, evaporation slows, which means there's less moisture cycling through the atmosphere. This can lead to drier conditions in some regions, particularly in the tropics, and shift the position of monsoon systems. In short, a big eruption can temporarily throw a wrench into the Earth's climate machinery. It's worth noting that while large eruptions can cool the planet, they don't offer a long-term solution to global warming. The cooling effects fade after a couple of years as the aerosols settle out of the atmosphere. Moreover, the consequences, disrupted agriculture, extreme weather, and air travel chaos, are not exactly desirable side effects. In fact, some scientists have studied these volcanic cooling events to better understand the potential risks of geoengineering strategies, like injecting aerosols into the stratosphere to counteract climate change. It's a bit like learning how a parachute works by studying what happens when someone is ejected from a volcano. Useful, but not ideal. Volcanoes can also affect the climate in subtler ways. Over geological timescales, repeated eruptions, especially large ones like the Siberian traps or the Deccan traps, can release enormous amounts of carbon dioxide, contributing to greenhouse warming. These flood basalt events, which span thousands or even millions of years, are linked to mass extinction events in Earth's history. While they don't create the short, sharp cooling of a Pinatubo or a Tambora, their slow-burning effect can gradually tip the climate scales. But the atmosphere isn't the only thing volcanoes influence. They can also impact the oceans. When large amounts of ash and debris fall into the sea, they can alter the chemistry of the water, sometimes triggering blooms of phytoplankton. These tiny marine organisms are the base of the ocean food web and play a major role in carbon cycling. In this way, volcanic eruptions may indirectly affect the amount of carbon dioxide being absorbed by the oceans. There's even evidence that volcanic eruptions can influence El Niño and La Niña events, those periodic shifts in ocean temperatures that affect weather patterns around the globe. After a major eruption, the cooling of the atmosphere can slightly adjust the temperature gradient across the Pacific, nudging the climate toward a La Niña pattern. This can mean wetter conditions in some areas, drought in others, and more active hurricane seasons in places like the Atlantic Ocean. Of course, not all volcanoes influence the climate equally. A gentle Hawaiian lava flow might be spectacular, but it doesn't toss much sulfur dioxide into the upper atmosphere. It's the explosive eruptions, particularly those near the equator, that have the biggest impact. Eruptions near the equator can spread aerosols more evenly across both hemispheres, amplifying their cooling effects. High-latitude eruptions, on the other hand, tend to keep their particles closer to home, affecting regional weather more than global climate. Timing also matters. An eruption that occurs during an already cold year might tip conditions toward crop failure, famine, or social unrest. Some researchers have even connected volcanic events to shifts in human history. For example, an eruption in the 6th century, possibly in Central America or Iceland, is thought to have contributed to what's known as the Late Antique Little Ice Age, a period of widespread cooling, famine, and societal upheaval in Europe and Asia. Records from the time describe a sun that refused to shine, crops that failed, and temperatures that felt more like winter than summer. But while volcanoes can cause hardship, they can also inspire awe. Some of the most vivid and poetic descriptions in historical records come from people who witnessed the strange skies and golden sunsets that follow a major eruption. Artists from J.M.W. Turner to Edvard Munch captured the eerie beauty of post-eruption skies. It's a reminder that even in their most destructive moments, volcanoes have the power to create, if not new land, then new light. Today, scientists continue to study volcanic aerosols and their climate effects using satellites, atmospheric models, and ice cores. These frozen time capsules preserve layers of ash and sulfur from past eruptions, allowing researchers to track volcanic events going back thousands of years. By matching ice core data with tree rings, written records, and sediment layers, scientists can reconstruct how specific eruptions affected global temperatures and weather. It's a bit like planetary forensics, piecing together the clues left behind by ancient eruptions to better understand the rhythm of Earth's climate system. And that rhythm includes more than just human influence. It includes tectonic shifts, orbital changes, and yes, the occasional sulfur-spewing mountain letting off steam. So the next time you look up at a particularly beautiful sunset, or notice the seasons behaving a little strangely, spare a thought for the volcanoes. They're not just geological curiosities, they're climate players, sometimes quiet, sometimes dramatic, always connected to the grand system that keeps our planet habitable. They remind us that Earth is not static. It breathes, erupts, and occasionally hits the cosmic reset button, sending its smoky signals high into the sky, where they drift, swirl, and change the world below. If there's one thing volcanoes are known for, it's destruction. Lava burying towns, ash choking the sky, whole landscapes transformed in a matter of hours, but that's only half the story. Because after the smoke clears and the ground cools and the last echo of the eruption fades into the distance, something remarkable begins to happen. Life comes back, quietly at first, tentatively, but steadily, persistently. In fact, volcanoes, for all their fiery flare and explosive behaviour, are also among the most potent forces of creation on our planet. To understand how this works, let's start at the most basic level: rock. When lava cools, it forms new rock, fresh, unweathered, and often barren. It doesn't look like much. A jagged field of basalt, black and sharp and lifeless. It feels inhospitable, and for a little while it is. But it won't stay that way for long. The first pioneers to move into these new volcanic landscapes aren't deer or birds or even insects. They're microbes, tiny, tough, and not at all fussy about luxury. Certain types of bacteria and archaea can survive on bare rock, feeding off minerals, sunlight, or even gases released from the cooling ground. These microbes form biofilms and begin the slow work of breaking down the rock, turning it into something more hospitable. In some cases, they can even fix nitrogen, an essential nutrient for life, which helps set the stage for more complex organisms to follow. Next come the lichens. These fascinating little life forms are actually partnerships between fungi and algae or cyanobacteria. The fungus provides structure and moisture retention, while the algae or bacteria photosynthesize, producing food. Together they cling to rock surfaces, slowly etching into the stone with weak acids. Over time, they help weather the rock into particles small enough to be considered soil. It's a long process. Think decades rather than days, but it's incredibly effective. Mosses and liverworts often follow, adding more green to the landscape. As these early colonizers live, die, and decompose, they build up organic material. Slowly, a thin but viable layer of soil begins to form. Now the door is open for grasses, ferns, and small shrubs. With each generation, the soil deepens, nutrients accumulate, the ecosystem gains complexity. In a few hundred years, that lifeless lava field may be a grassy plain. In 1,000 years, it could be a forest. In a few thousand more, it might host birds, mammals, insects, and the full richness of a mature ecosystem, all built from nothing more than volcanic rock and time. This process is called primary succession, and volcanoes offer one of the clearest examples of it in action. The idea is simple. Start with a blank slate, no soil, no life, and watch how nature rebuilds from scratch. It's one of the most hopeful processes in all of ecology. Proof that even after devastation, life not only returns, it thrives. One of the best studied examples of this comes from the island of Surtsey. In 1963, a submarine volcano off the southern coast of Iceland erupted and built itself an island over the course of several months. By 1967, Surtsey was a fully formed landmass, officially recognised by the Icelandic government, and then scientists closed it off to the public, turning it into a living laboratory. They wanted to see exactly how life would colonise this brand new island, untouched by human influence. The first arrivals were mosses and lichens brought in by the wind. Then came seeds carried by ocean currents or deposited in bird droppings. Insects arrived, likely blown in from the mainland. Birds followed, first as visitors, then as residents. By the 1980s, Surtsey had its first nesting seabirds. Today, it hosts a growing number of plant and animal species, including grasses, bushes, beetles, and gulls. And all of it started from bare rock. Another stunning example is found in Hawaii. The Hawaiian Islands are volcanic in origin, built over millions of years by a stationary hotspot beneath the Pacific Plate. As the plate moves northwestward, new islands are born over the hotspot while older islands erode and sink. This means each island is at a different stage in both geological and ecological development. On the Big Island, where Kilauea has been erupting on and off for decades, you can see fresh lava fields only a few years old, right next to lush rainforests that have had thousands of years to grow. Walk across these landscapes, and you're essentially walking through time, witnessing the stages of ecological succession in real life. Volcanic soil, once it has formed, is incredibly fertile. This might seem counterintuitive. After all, lava isn't exactly known for being cuddly. But as it weathers, it releases key minerals, iron, magnesium, potassium, calcium, that plants love. Combine that with regular rainfall and a warm climate, and you've got ideal growing conditions. This is why many volcanic regions are densely populated and heavily farmed. Think of the vineyards on the slopes of Mount Etna in Sicily, or the lush rice paddies surrounding Mount Merapi in Indonesia, or the coffee plantations near Mount Kilimanjaro in Tanzania. Volcanic soil supports agriculture that, in turn, supports civilizations. But volcanoes don't just rebuild ecosystems, they also build land. Every island in the Pacific was once a volcano. Many still are. The Galapagos, home to some of the most unique species on the planet, are volcanic islands. So are the Canary Islands, the Azores, and parts of Japan. Without volcanoes, Earth would have far fewer places to live, grow, and explore. Even underwater, volcanoes create habitats. Hydrothermal vents on the ocean floor support entire ecosystems in total darkness. They provide heat and nutrients in otherwise barren environments. Tube worms, clams, shrimp, and bacteria flourish around these vents, forming the foundation of the food web that doesn't rely on sunlight at all. Life, it seems, has a knack for finding a way. Some researchers believe that these hydrothermal vent systems may even be the cradle of life on Earth. The combination of heat, water, and chemistry creates ideal conditions for the formation of organic molecules. Perhaps the very first life on our planet didn't crawl from the sea to the land, but instead burbled up from a volcanic crack at the bottom of the ocean. Volcanoes may even play a role in stabilizing Earth's climate over long periods. The carbon dioxide they emit helps regulate the greenhouse effect. Too much carbon dioxide and the planet warms. Too little and we freeze. Over millions of years, volcanic emissions and the weathering of volcanic rock help maintain this delicate balance. And volcanoes aren't just functional, they're beautiful. Strange, perhaps, but undeniably beautiful. A volcanic crater filled with turquoise water, a black sand beach at sunset, a steaming fumarole in the middle of a snowy field. These are places of wonder, places that remind us of the Earth's raw power and its boundless creativity. They inspire art, mythology, and science. They remind us of destruction, yes, but also of resilience. The forests that grow back, the animals that return, the people who rebuild, the soil that bursts with colour after the fire is gone. In some cultures, volcanoes are considered gods. In others, they're seen as portals to the underworld. But in every case, they are acknowledged as forces of both fear and respect. And maybe that's the right way to see them. Not as villains or heroes, but as something more ancient and elemental. Something that doesn't care about human timelines, but still gives us the chance to start fresh. So the next time you see a lava flow on the news, or walk across a hiking trail with a view of a distant volcanic cone, remember this. Beneath the surface destruction, there's potential. Potential for renewal, for life, for something new to take root. Volcanoes are not just the end of a story, they're often the beginning. After all, what better metaphor for life itself? Sometimes things fall apart, sometimes everything burns down, but given time, patience, and just the right combination of sunlight and microbes, something green begins to grow again, something unexpected, something beautiful, something alive. And now, as the final wisps of steam rise from our volcanic journey and settle into the cool night air, we come gently to a close. We've wandered through molten hearts and frozen geysers, stood at the edge of craters and peered into the dark oceans of distant moons. We've listened to the whispers of Earth's inner chambers and watched the sky grow strange under the influence of distant ash. From the very first spark of life to the sculpting of new lands, volcanoes have proven themselves to be both destroyers and creators, fierce, majestic, and often misunderstood. All of this, and yet we've barely scratched the surface. The earth beneath our feet is still moving, still shifting, still breathing heat and pressure into every crack and fold. Volcanoes are not just relics of a wild past. They are part of our present. They shape our landscapes, influence our climate, and remind us, sometimes quite loudly, that this planet is alive. So as you lie back now, maybe with eyelids growing heavy and thoughts drifting like lazy plumes of steam, I'll gently ask what I asked at the beginning. Where are you listening from? What time is it there? Midnight, 2 a.m. Perhaps you're on the other side of the world where the sun is just starting to rise. Either way, I hope you found this time to be relaxing, fascinating, and just engaging enough to carry you to the edge of sleep, without dragging you into the heart of a lava lake. And if I've kept you awake with tales of boiling seas and icy volcanoes on Saturn's moons, well, at least you've learned something. If you've enjoyed this journey with the Sleepy Scientist, I'd be so grateful if you could leave a like, tap that subscribe button, and let me know in the comments where you're listening from. It's always a joy to know who's out there, drifting through science and sleep with me. Sweet dreams, and may your inner earth stay peacefully dormant tonight.